Hello from R Charts. In this video I will explain how to perform optimization of continuous functions of a closed bounded region. Let's dive in. What we are dealing here with is a real function of several variables that we wish to maximize and minimize subject to constraints that determine a closed bounded domain. First, we really need to assume that this function is continuous, otherwise there might not be minima or maxima at all. By the extreme value theorem, a continuous function defined over a closed bounded region has somewhere over this region its maximum and also its minimum, but they are not necessarily unique. Now, there are two options where such extrema might be: in the interior of the domain or on the boundary of the domain. Wait, what is boundary and what is interior? Topologically, a point lies on the boundary of a set S if every open set O containing the point has both points inside and outside of the set S. Interior is the union of all open sets that are subsets of the set S, and thus it is itself an open set. For example, consider a continuous function of two variables x cubed plus y cubed minus x squared minus y squared that we wish to optimize subject to x squared plus y squared being less than or equal to 1. The region given by the constraint is a filled circle, a closed bounded domain. It can be decomposed to its interior, x squared plus y squared being less than 1, which is an open set, and the boundary, x squared plus y squared being equal to 1, which is given by an inequality constraint. Since the function is continuous, by the extreme value theorem, it has some global extrema. Let us first search for extrema in the interior, an open set. I will explain to you a general procedure how to find extrema over an open domain before we go back to our particular example. To apply calculus, I first assume that the function has continuous second-order partial derivatives. By looking at where the gradient is 0, we will find a critical point C. If we are lucky, and the function is either strictly convex or strictly concave, or at least quasi-strictly convex or quasi-strictly concave, then we are done, and at the critical point C, we must have the global minimum or maximum, minimum for convex functions, and maximum for concave functions. Wait, what is a quasi-convex function? Quasi-convex functions generalize convex, U-shaped functions. Given that the interior is a convex set, the function will be quasi-convex if and only if the set of points S that gives smaller or equal function values than a given point C is convex. For this, it is sufficient for the gradient of f at C to have an obtuse angle with all vectors going from C to any point of the set S. If we are not lucky, we need to look at the Hessian matrix, which we obtain by neatly arranging all second-order partial derivatives. Do you remember that we wanted these derivatives to be continuous? Do you know what that implies about the Hessian matrix? Let me know in the comments! If the Hessian at C is indefinite, there is no extremum but a saddle point at C. If the Hessian is positive definite or negative definite, we have an evidence that at C there is a local minimum or a local maximum, respectively. In fact, at that point we can still have a global extremum, but we just do not know without further evidence. Let's employ this procedure to our example. First, the gradient is 0 when both partial derivatives are 0. This happens in the following 4 points: 0, 0, 2/3, 2/3, 0, 2/3, and 2/3, 0. They all lie in the open domain given by x squared plus y squared being less than 1, so we have 4 critical points to test. Now, since the function is neither convex nor concave, let us find the Hessian matrix. Differentiating the highlighted partial derivative according to x gives us 6x minus 2. Since there is no y, differentiating it according to y gives us 0. Differentiating the other partial derivative according to x gives us again 0, there is no x. But differentiating it according to y gives us 6y minus 2. Now we substitute our 4 critical points in place of x and y in this matrix. For 0, 0, we obtain a negative definite matrix. At 0, 0 there is a local maximum. For 2/3, 2/3, we obtain a positive definite matrix. At 2/3, 2/3, there is a local minimum. Finally, at both 2/3, 0 and 0, 2/3, the matrix is indefinite. Notice that its determinant is negative. There are saddle points, no extrema. Now we look for extrema at the boundary, which is given by an equality constraint. As before, I will first explain to you a general procedure how to find extrema with equality constraints before we will look at our particular example. Since we here deal with equality constraints of the form g equals 0, we extend our assumption on continuous second-order partial derivatives also to these functions g. Then we employ the method of Lagrange multipliers to find a critical point c. If you are double lucky, and not only the considered function f is either strictly quasi-convex or strictly quasi-concave, but also the region defined by the equality constraints is convex, then we are done, and at the critical point c we must have the constraint global minimum or maximum, minimum for convex functions, and maximum for concave functions. Wait, what is a convex region? Does it have to do anything with convex functions? No, it has nothing to do with convex functions. A set S is convex if a line segment joining any 2 points from S lies completely in S. The first circle shown on the screen is a convex set, but its boundary alone is not. If we are not lucky, it might be helpful to look at the Hessian matrix, which has Lagrange multipliers as parameters, but this might not be enough. Even if this matrix is indefinite at C, we still might have a local extremum at C. Checking definiteness of a matrix is the same as asking whether the corresponding quadratic form is positive or negative for all non-zero vectors H. But when we have constraints, we do not care about all vectors H, only about those that are perpendicular to the gradients of functions g that were used to express constraints. Moving in other directions would get us out of the region defined by the constraints. So if the quadratic form at C is positive or negative for all non-zero vectors H that satisfy the perpendicularity condition, recall that vectors being perpendicular is equivalent to the dot product being 0, then we have at C a local minimum or maximum, respectively. We will now return to our example. We have only one equality constraint expressed as a function g, which is x squared plus y squared minus 1. The method of Lagrange multipliers results in 6 critical points. For example, if y is 0, it must be that x is either 1 or negative 1 to satisfy the constraint. The Hessian matrix must be evaluated for this and other options. As a demonstration, let me pick x equals 1. In this case, the Lagrange multiplier must be half. Substituting these numbers to the Hessian, we obtain an indefinite matrix. No need to worry. Rewriting it as a quadratic form, we obtain 3h1 squared minus 3h2 squared, which can be both positive and negative, depending on h1 and h2. The additional condition, however, gives h1 equals 0, otherwise we would move outside the region, in which case we obtain a negative expression, unless, trivially, h2 equals 0. We may conclude that at the point 1, 0, there is a constrained local maximum. At this point we have an exhaustive list of all possible candidates for extrema, so we compare their function values to find the final answers. Among 4 candidates from the interior and 6 candidates from the boundary, we identify 3 global maxima at 0, 0, 0, 1, and 1, 0, and 2 global minima at negative 1, 0, and 0, negative 1. And here you have it! Optimization of a closed bounded region in one mod chart. Best wishes from our charts!